Hello everyone and welcome back to Diksha Karnataka YouTube channel, and you are watching KCET 60 out of 60 in physics. Here we are discussing all the chapters, all the concepts, all the PYQs so that you can get 60 out of 60 in KCET 2025 when you are appearing. Now we have already completed discussions of 3 chapters. Now we are starting with 4th chapter today, that is moving charges and magnetism. And in this chapter we are specifically discussing different types of magnetic forces, also force on a moving charge. Now to get all the latest update, you have to join our WhatsApp channel. Link is given in the description. If you are joining our WhatsApp channel, you will get, whenever I am posting one video, that link will be available in our WhatsApp channel. Also during weekend we are conducting a test series absolutely free of cost. You can download the question paper from our WhatsApp channel, you can solve it, and you can check the answers in the evening when I am doing the solutions. Now let's start with today's topic, what all we are going to discuss. So first we are going to discuss with Lorentz force. Obviously there will be a brief introduction as well. After that introduction we are going to discuss about Lorentz force. Then we will discuss magnetic force on a current carrying conductor, and then we are going to discuss motion of a charge in magnetic field. All these 3 concepts are very important. Also we will solve a few examples and some homework problems that we have given you yesterday. Now let's start with the introduction. So we know that whenever there is a current, okay, or moving charge, basically there is an magnetic field associated with it. Okay, so moving charges or currents produce a magnetic field in the surrounding space. So normally if the charge is static, suppose I have a charge which is static, okay, there is no magnetic field associated with it, only electric field is associated. Okay, so we know that electric field, everything's electrostatic field we have calculated, right? But as soon as it starts moving, not only the electric field will be there, and based on the position of the charge it will instantaneously change. Okay, it will no longer be constant, but it will change. But when it is moving, not only electric field, magnetic field also be produced. Okay, moving charges produce magnetic field. Now the moving charges produce magnetic field. Now if you consider the moving charge is moving out of the page, this is the symbol out of the page, and cross is the symbol into the page. You should remember these symbols, very important, very handy whenever you are attempting, suppose you are attempting your board exam, board exam, and you have to draw something into the page, out of the page, then this is very important that you remember these symbols. Okay, dot means out of the page, cross means into the page. Now suppose it can be a moving charge, single charge, okay, or it can be a lot of charges moving, that is current carrying conductor. So we know that current carrying conductor is basically charges moving in a direction. Okay, when there is a current carrying conductor also produce magnetic field, because basically current means it's a flow of charge, right, flow of electrons. So current carrying conductor can also produce magnetic field. Now whenever there is a charge, okay, out of the page or into the page, based on the polarity of the charge as well, you can see what is the direction of magnetic field. So for example, this is an electron. Okay, suppose this is an electron and it is moving out of the page. In that case you can say the charge will be opposite. Okay, and if it is a proton or it's a positive charge, suppose positive charge, proton is coming out of the page, then the magnetic field will be like this. Okay, so we will generally consider the direction of positive charges. For example, when we are considering current, we generally consider the conventional direction of current. Okay, so conventional direction of current is actually opposite to that of electron. We already learned that. So whenever suppose a positively charged particle is moving out of the page, then the electric magnetic field will be like this. And so we can say this is north pole, this is north pole, this is south pole. Okay, so magnetic field lines will be like this. Magnetic field line, there are magnetic field lines. We will learn about the properties of magnetic field lines in our subsequent videos as well. But for now, we should remember that you can construct magnetic field lines like this, and they will move in the direction like this. Okay, so magnetic field lines are like this. Similarly, when it is into the page means in this direction. Suppose again a proton is moving into the page, then the corresponding magnetic field will be like this. Okay, and here it is a extensive view where all, as you are moving away from the center, you can see the magnetic field lines are still there. Okay, so magnetic field exists everywhere in the space. Now, whenever there is a magnetic field, we can expect when there is an electric field, what we expected. So we started with magnetic force, then we moved into magnetic field. Here we are doing opposite because we are already aware of the field. So whenever there is a field, there should be a force. Now what is the force is given by? So first of all, whenever there is a external electric field, okay, so suppose we have an external electric field. So field is always associated with force. Force is always associated with field. Any type of force except frictional force, any non-contact force. Whenever you are talking about any non-contact force, generally it associated with a force. Okay. Now, suppose we have a electric field and we keep one positive charge, say Q here. Then I already explained that this charge will experience a force in the direction opposite to the force field. Is it? It will experience a force in the direction of electric field. You should remember, if the charge is positive, it experiences a force in the direction of electric field, not opposite. Okay. And when the charge is negative, it experiences a force opposite to that of the electric field. So in general, we can write this force as QE. If Q is positive, it will be automatically in the direction of electric field. If it is negative, automatically it will be opposite to that of the electric field, right? So this is the force on a charge kept in an electric field. Now, this charge can be static, this charge can be moving. It does not depend on the motion of the charge. Force will be at any point, the value of electric field at that point and multiplied by the charge. It is independent of the motion of the charge. Okay, this electric force. But magnetic force depends on the motion of the charge. It is given by V cross V. What is the meaning of V? V is the force with which the electric charge is moving. Okay, the force with which the charge is moving, and we know that velocity is a vector quantity. So V cross B. Okay, so suppose electric field is in this direction, magnetic field is suppose in another direction. Magnetic field, suppose this is the direction of E, this is the direction of B. Okay, now V cross B means, first we have to align our hand in the direction of V. Okay, then we will rotate our hand towards B. Cross product, right? Cross product means first we will start with the first vector, whatever vector is first. So we will start in this direction, then we will rotate our hand towards the second vector, okay, in the shortest possible path, and then whenever our thumb is pointing out, that will be the direction of the field, right? So V cross B is the direction of the magnetic force on the charge. Okay, this is the direction of magnetic force. This is the easiest way to remember. There someone use palm rule, some other rule, but this is the easiest way to remember the direction of the force. So rotate your hand in the direction from first vector towards the second vector in the shortest possible path. Then whenever your thumb is pointing out, that is the direction of the field. So in this case, the force will be in the direction into the page. So we can write this as like this. This is the direction of magnetic force. Now, when we combine these two forces, there are two different forces acting on a same charge particle. Okay, so the net force acting on the charge is given by Q common. If you see, Q is common. Okay, E plus V cross B. Now, if the charge is static, what is the force? If the charge is static, basically V is 0. V is 0 means it will be only V cross B. Okay. Now, force on a negative charge is opposite to that on a positive charge. As I explained, force on a negative charge is opposite to that of the positive charge. So basically, this right hand rule that I taught you is basically for positive charge. If the charge is negative, you can find the direction for positive charge, then you just reverse it. because it is minus, right? So the rule that I taught you using the right hand is only valid for positive charge, not for negative charge. Negative charge will be opposite to that, right? Now, a vector product makes the force due to the magnetic field vanish become 0. Vanish means become 0 if velocity and magnetic field are parallel or antiparallel. Suppose magnetic field is in this direction, okay, magnetic field is in this direction and object is also moving in this direction, the charge, okay, the charge is also moving in this direction. In that case, the magnetic force will be 0. Similarly, if the charge is moving in this direction also, this is parallel, this is anti-parallel. In both cases, magnetic force will be 0. Generally, for only magnetic force, we write it like FB, because magnetic field is denoted by symbol B. Electric field is denoted by the symbol E. Magnetic field is denoted by the symbol B. Okay. Okay. In this case, obviously, there is no magnetic force. So, if you want to avoid magnetic force acting on you, then you have to move parallel to the direction of magnetic field. Okay. The magnetic force is 0 if the charge is not moving, that is V equals to 0. I told you multiple times, we know that FB is basically Q V cross B, okay, or in scalar form it is Q V B sin theta. Okay, so how can this force be 0? This force can be 0 either if the charge is 0, or the speed is 0, or the magnetic field is 0, or sin theta is 0. Now, charge is 0 does not make any sense. You are calculating force on a charge and you are saying the charge is 0. So, that is no longer a charge. Obviously, this is not applicable. Other way, velocity can be 0, the charge is static charge. Static charge is very much possible. So, in that case, magnetic force is 0. Also, you are saying force acting on a charge when kept in a magnetic field. So, magnetic field 0 does not make any sense. Okay. So, other sensible thing is sin theta is 0. Okay. So, when sin theta is 0, sin theta 0 means theta equals to 0 or theta equals to 180 degree. In both cases, theta is 0, sin theta is 0. So, in both cases parallel or anti-parallel, and second one is when velocity is 0. Okay. So, it will they will not experience any magnetic force. Okay. Now, let us solve one problem, very interesting problem. A proton moves with a velocity of 5 times 10 to the power of 6 j cap meter per second. Okay. So, the velocity is given by 5 times 10 to the power of 6 j cap, sorry, j should be small letter, right? And electric field is given by 4 times 10 to the power of 6 2 I cap plus 0.2 j cap. This is from one of the previous year problem. We might solve it again once we are doing PYQs, but that time I will solve it in a shortcut way or in a faster way. Okay, I will skip some detail that time because it is already solved in the lecture. And magnetic field is given by 0.2 times I cap plus 0.2 j cap plus k cap. Now, to solve this problem, okay, you have to remember that few things, that cross product. If you remember the term cross product, and if you remember the things related to cross product, that when we are doing cross product, we use this circular rule I j k, right? I cross j equals to k, and k cross I equals to j, and anything opposite to that is negative, right? So, j cross I is minus k. Okay, k cross j is minus I. So, only when we are going in this direction, we are getting the third quantity as positive. Okay, I cross j is k, k cross I is j. Okay, and if you are going in the opposite direction, that is k cross j, then it is minus I. Also, I cross I is 0, j cross j is 0, k cross k is 0. Okay, These are the things that you need to remember. We are not going to use matrix method or determinant method. We will, because this is very simple. Okay. Now, first of all, we have to find the electric force and magnetic force. Electric force, we do not need to worry too much about electric force. Why? Electric force is nothing but, if you are only writing the electric force, it is nothing but charge of a proton times electric field, right? It does not depend on the velocity. If you remember that, okay, charge of a proton is 1.6 times 10 to the power of minus 19, same as electron, right? Only thing is it is positive, for electron it is negative. Now, what is the magnetic force? Magnetic force is charge times V cross B, right? So, what we have to do? We have to find V cross B first. Okay. So, first we will find V cross B. So, if you see, V is j cap. Okay. So, what we will do, and this value is a constant, scalar constant. So, we will write this as 5 times 10 to the power of 6. This is a constant, and 0.2 is common from B as well. So, we will write all the constants first. Okay, all the constants that is common, that I will write first. Now, next is V cross B, that means J cross I. Starting first number is J cross I. Now, what is J cross I? J cross I means this way. J cross I, that means it should be minus K, right? So, minus K, and the magnitude will be, there is only 1 is here. So, only 1 minus K. Okay. Now, next is J cross J. So, this term should goes to 0, right? J cross J is 0, and last but not the least is J cross K. J cross K means J cross K, that should be equals to I. So, V cross B also we have calculated, right? Next is only put the values and calculate the answer. So, the total force should be electric force plus magnetic force, that is, we can take E common. Electric field E, what is the value of electric field E? Electric field E was 4 times 10 to the power of 6. Okay. 2 I cap, 0.2 J cap, 0.1 K cap. Okay. 2 I cap plus 0.2 J cap plus 0.1 K cap, right? Now, next is magnetic field V cross B. Next, E we have taken common, right? So, only V cross B value that we are interested. V cross B, if you simplify it little bit, 0.2 times 5. 0.2 times 5 means what? 1, right? It will be 1. So, 1 times 10 to the power of 6. Basically, you can simply ignore this 1, and you can simply write 10 to the power of 1 times I cap minus K cap. Okay. So, just write the value. Okay. Now, simplify. So, to simplify, let us take the 10 to the power 6 common. Okay. So, E times 10 to the power of 6, we will calculate the value of E at the last. Okay. Now, 4 is here. So, 4 times 2, 8 I cap plus 4 times 0.2, 0.8 G cap. Okay, plus 4 times 0.1, 0.4 K cap plus this 10 to the power 6 is common, 1 I cap minus 1 K cap. Okay. Now, rewrite the values. 1.6 times 10 to the power of minus 19. Now let us put the values here. 10 to the power of plus 6. 1, 8 plus 1, that is, here it is 1, right? Nothing is there means 1. 8 plus 1 is 9. 9 I cap plus, there is no j here, only one j, so 0.8 j cap. 0.4 minus 1, here also 1, so 0.4 minus 1 means minus 0.6 k cap. Now they have asked you to find the magnitude of it. Okay, they have asked you find the magnitude. Now you see that this is only the largest number, these are very small numbers. Now we know that magnitude of any vector a I cap plus b j cap plus c k cap. Okay, the magnitude of this is given by square root of a square plus b square plus c square. So magnitude of this force is basically 1.6 times 10 to the power of minus 13. Okay, minus 19 plus 6 is 13, square root of 9 square plus 0.8 whole square plus 0.6 whole square. This minus sign does not matter as it is inside the whole square, so it will be converted into plus positive. Now if you see that these two numbers are very small compared to this number 9. Okay, so what approximately, to do approximation, what we will do, we will ignore all these two values. So what we will do, you only consider 1.6 times 10 to the power of minus 13, 9 square, that is 9 times 1.6 times 10 to the power of minus 13. Okay, so it will be 9 54. 9 plus 54 is 14.4. Right? So how did I do? 9 times 9 ones are 9. 9 times 0.6 is 5.4. 9 5 6 are 54. 54 and there was 1 point, so it will be 5.4. Now 9 plus 5.4 is 14.4. This is the easiest way to calculate. Now let us check the answers. What was the answers? So from the answers given, you can see this is the closest answer given from the calculated value. We did some approximation, so we can easily say this is the correct answer. Okay, so you have to be smart while doing approximation, you have to be careful, and while calculating you have to be faster. Okay, this is little longer problem. If you are not practicing cross product and dot product, maybe you will be facing difficulties, even though first few concepts are concepts are not coming directly, but indirectly they are coming. Okay, so you have to be careful and answer accordingly. Now let's move on to our homework problem. So first homework solution. So if you see this point, this structure is what? This is point A, this is point B. So basically this is a Wheatstone bridge structure. I already told you, if this is P, this is Q, this is R, this is S, then we have to check if this condition is satisfied or not. P by Q equal to R by S. Okay, if this condition is satisfied, then we can simply ignore the mid resistance, right? Now if you see 3 by 6, what is 3 by 6? 3 by 6 is half, right? Now what is 4 by 8? 4 by 8. This is also half. So not always they will be equal. Don't expect that they will give you equal values every time. They sometimes may give you values like this, 3 and 6, 4 and 8 here. Okay. So in this case, as you can see, 3 and 6, 4 and 8, they are equal values. So they are cancelling each other. So what we not cancelling, they are getting equal. So we can say they are obeying this relationship, P by Q is equal to R by S. So we can simply say, okay, this resistor is no longer connected, so we can simply ignore this. Okay, So you have to be careful and you have to be smart while checking this condition. You don't need to calculate it like the way I did. You should see, okay, 3 by 6 is half, 4 by 8 is half, so they are satisfied. So it is, you don't need to calculate this, you just need to check, and if you are sure, okay, this is done, then you can immediately remove this resistance, and you can think about the equivalent resistance. What is the equivalent resistance? 3 and 4 are in series. Okay, 3 and 4 are in series, and then 6 and 8 are in series as well, and the entire thing is in parallel. So 3 plus 4 is 7, okay, and 6 plus 8 is 14. So they are in parallel. So 7 and 14 are in parallel. So equivalent resistance will be 7 times 14 divided by 7 plus 14. That is 7 plus 14 divided by 21. 3. So 14 divided by 3. So it will be 14 by 3. That is the answer itself. They have not given you decimal answers. They have asked you what is the value, and if you calculate this up to this point, 14 by 3 is directly you are getting the answer. Say very simple problem, okay. So you have to answer such questions. This is a very common KCET question. You should be able to answer these questions without anyone's help. Now next question, in the following network potential at O. So what we are trying to find is the potential at O. Suppose potential at O is VO. Okay. Now if you see here, the potential is 8. At this end potential is 4. At this end potential is 2. Okay. So it is given such a way that you can identify the direction of current. So from this branch current is flowing in this direction. So I will say I1. Okay. From here to here current should flow in this direction, I2, and from here to here current should flow in this direction, and I say I3. Okay. Now at the junction O, if I apply KVL or junction rule, okay, junction O, if I apply junction rule, then we can write I1 is basically I2 plus I3. Simple, right? So this is done. This is KCL part is done. Next we will apply simple Ohm's law. What is that? Potential here was VO. Potential at this point is 8 volt. So if you remember Ohm's law, potential at this point was VA, potential at this point say VB, and resistance is R, then current was VA minus VB by R. If you remember that, current is flowing in this direction. So that was the Ohm's law. In your 10th class 10th you have learned this, right? So similarly here also we will apply the oldest form of Ohm's law that you have learned. So current is flowing from higher potential to lower potential. If you remember that, current always flows from higher potential to lower potential. So I1 is 8 minus VO divided by the resistance 2 ohm. Okay, equals to, now what is I2? Here also current is flowing from higher potential to lower potential. So VO minus 4 divided by the corresponding resistance 4 ohm. It is a little trick that you need to learn. Okay, here to here current is flowing from O to C. So VO minus 2 divided by 2. This is a little trick that you have to learn. These are the specific tricks that you have to learn to solve specific problems. Now if you see, there is 2, there is 4, there is 2. So the largest number is 4. So if we multiply everything with 4, we will get 2 times 8 minus VO equals to VO minus 4 plus 2 times VO minus 2. Okay. So because we are multiplying with 4, so this, there will be an 2 extra, there will be a 2 extra, but this is only VO minus 4. Okay. Now let's continue. So we can write this as 16 minus 2 VO equals to VO minus 4 plus 2 VO minus 8, right? Let's check it once. So 2 VO minus 4, sorry, 2 VO minus 4. Okay, now simplify. 16 minus 2 VO equals to VO plus 2 VO, that is 3 VO minus 4 minus 4 minus 8. Okay, now take this VO on the other side. So 3 VO plus 2 VO equals to, now take this in this side, 16 plus 8. Okay, so it will be 5 VO should be equals to 24, or VO should be equals to 24 by 5. That is, you can cancel this, you can multiply 2 here, multiply 2 here, 48 by 10, so 4.8. Okay, and the answer is 4.8. If you check, so option D is correct. Those who have answered option D, I have said correct, but none of you have done it so far. Okay, now next is magnetic force on a current carrying conductor. Suppose we have a conductor like this, and it is carrying a current, say I. Okay, and it is kept in a external magnetic field, say B. There is a magnetic field at some direction, say B. Okay, then what will be the force acting on this conductor? Because we have studied individual charges. Now instead of individual charges, we have a full conductor. Conductor is full of charges which is carrying current, so it is obviously facing a force. Individual charges are experiencing a force, and that individual charges are within the conductor, so conductor itself will experience a force. Now that force is given by F is equal to I L cross B. What is the meaning of L? L is the length of the conductor which is exposed in the magnetic field. Now if you see, we have mentioned L as vector. Now what is the direction of this L? L is basically in the direction of the current. L is the direction of the current, and in short we can write this force as Bill sin theta. Okay, you should remember Bill. Okay, whatever way you can want to remember, you can remember as a bill of electric bill, or telephone bill, or gas bill, or during our time we used to remember as Bill Clinton. During my time, the president of US was Bill Clinton, and he was very famous person. Okay, every day in newspaper article used to come about him. So our sir said Bill Clinton, you should remember Bill Clinton. So force on a current carrying conductor is given by Bill sin theta. Okay, no matter how you can remember, you have to remember this formula. This formula going to be very, very important. Okay, now now we are talking about moving charges in an magnetic field. A charge moving in an uniform magnetic field will experience a force. Obviously, if current is experiencing a force, charge should also experience a force, right? Now how it will experience a force, this is very, very interesting. Okay, this force acts as a centripetal force and produces a circular motion perpendicular to the magnetic field. So let's see what is that. Suppose we have a charge. We have a charge which is moving in this direction. Okay, so the force is charge is moving in this direction. Now we know that the force will be FB will be equals to Q V cross B, right? That was the Lorentz force that we already learned. So it is nothing new, but it is essentially when we are talking about a charge moving in a particular direction, what will happen? Only there is no electric field, only magnetic field is there. What will happen to that charge? So the charge was trying to move in this direction. Okay, and magnetic field was inside into the paper. So the charge will experience a force which is pointing in this direction, right? So start with V, move towards B. Okay, start with direction of V upward. B is into the paper. So move in the direction of B, and you will get the direction of force acting on this charge. The force is basically in this direction, and what will happen as this V and F are acting like this, so it will eventually, as it is moving, it will start moving in a circular path. Okay, it will start moving in a circular path, and this force is basically providing the required centripetal force. We know that whenever there is a circular motion, someone has to provide the centripetal force. It can be tension, it can be gravitation. In this case, it is the magnetic force. Magnetic force is providing the centripetal force required for circular motion. Okay. Now, if the velocity has a component along B, so if it is directly perpendicular, okay, V and B are perpendicular. V is when V is suppose in this direction, B is inside the into the paper, so that is the angle is perpendicular. In that case, there is no component of V in the direction of B, because you cannot take, if you take the component, cos theta will be cos 90 will be 0. So in that case, there is no component. But if there is a component, suppose V is in moving in such a way that V and B are not perpendicular. So if V and B are not perpendicular, B is in this direction, B is on some direction where there is an angle, say theta, then you can take a cos theta component in the direction of B. That is important. You can take the direction in the direction of B. So you can take a projection, and you can say, okay, this is V cos theta. So what will happen in that case? In this case, when they are perpendicular, obviously it will start rotating in a circle. Okay, we will study in detail about what will be the radius of the circle, what will be the frequency of rotation, everything we will know. But if they are not perpendicular, but they have a component in the direction of B, in that case, okay, the component remains unchanged. So the perpendicular component will remain unchanged. So it will give rise to a motion of circular motion. But the component which is in the direction of B, that will not experience any change. So what will happen? This will in turn produce a helical motion. So let us understand that in detail. So in this case, as you can see, V has two components. One is parallel, one is perpendicular. Perpendicular component gives rise to the circular motion. Okay, and this will give rise to a linear motion in this direction. Okay, so we will get two motion. One is circular motion due to the perpendicular component, and due to the linear component or parallel component, we will get a linear motion as well. So basically, what we will get something like this. Okay, so circle is not in a single plane, but it is like this. This is called helical motion, like a spring. Okay, so this structure is called helix. Okay, the geometry of helix is not there in your syllabus. It is similar to that of parabola or hyperbola. There is an equation for helix as well, but that is not there in your syllabus. So don't worry about it. But you should remember this structure is called helix. Okay, it's like a spring. Now let us discuss about radius. As I said, radius, angular frequency, and time period of this motion. This is very important. These formulas, these equations are very important. Many a times objective questions and numerical questions for your board as well as KCET, this question comes. So let us understand this concept. So the radius of this circular path, radius means this is the radius, right? Or this is the radius. Any distance you can take, this is the radius. Any distance you take, this is the radius. So all this radius is given by mv by qb. So what is m? M is the mass of the charged particle, v is the velocity of the charged particle, q is the charge of the charged particle, and b is the magnetic field. Okay, so only thing that is confusing is m. Whose mass it is? It is the mass of the charge. Okay, v is velocity of the charge, q is the charge on the charge. Okay, now angular frequency, we know that linear velocity and angular velocity is related by this relation, v is equal to r omega, or omega is equal to v by r. Now if you put this value of r in this equation, you will get angular velocity will be qb by m. This is some important. Sometimes they will ask it is rotating at a certain angular speed, then what is the magnetic field or what is the charge. So in that case you can use this formula, right? And time period, this is another important formula. Time period we also know 2 pi by omega. So you can put the value of omega here. So the time period will be, in turns it will be 2 pi divided by qb, and m will go up. So 2 pi m by qb. Previous year questions, this formula is also very important. Okay, now there was one motion called cyclotron motion, which was given as an application of this motion, this force, but cyclotron motion itself is no longer there, but all the components which were asked as a cyclotron motion will still be there. So time period, they might ask a charge is given in a magnetic field of such and such magnitude, what will be the time period. Okay, so you have to use this formula to calculate the time period, but previously they directly ask as a form of cyclotron. So a charge is given in a cyclotron and a magnetic field this, what is the time period of rotation. But in this case cyclotron is not there, but these formulas are still there in your syllabus. So instead of asking cyclotron, they will directly ask you. Okay, so question will be very, very direct. Okay, now we have reached to the end of the lecture. So it's time for homework. I have selected 2 questions for today's homework. First homework is this: please pause the video, read the question, try to answer this in your notebook, and mention the answer in the comment below. This is very easy question. First question is very easy. Second question is little bit long and difficult. So if you are able to answer this question without any help, then obviously you are progressing in a correct way. You are obviously paying attention to the lecture. If you are paying attention to the lecture, also one more thing, to solve this question you need a diagram. I will provide the diagram to you, okay, because this question is not very clear. So the wire is not located like this, the wire is located like this. Okay, so the wire is located like this, and current is, suppose current is coming out of the page. So you can take into the page as well. Magnetic field is in this direction, magnetic field is vertical direction. Say current is out of the page. Okay, when I was trying to solve it, initially I was thinking the problem was like this, so, and I was not able to understand how it can balance the force. Okay, now you tell me, if I consider this the rod is like this and current is flowing through it, now what is my mistake? Why you cannot achieve an equilibrium in this structure, but you can achieve an equilibrium in this structure. Okay, so this is incorrect. This is incorrect. This is the correct diagram. Now check the diagram and answer the question and tell me the answer in the comment. Okay, and there is a dedicated playlist available for all the videos available in our channel. You can go and check all the videos, previous lectures, mock test question papers, mock test discussions, everything is available in the single place. And if you have not yet subscribed to our channel, please don't forget to subscribe to our channel, join our WhatsApp group. Okay, the link is given in the description, and share it with your friends. Thank you for watching this video. I will be back with the part 2 of moving charges and magnetism in tomorrow's video.